Okay, so now I am recording, and then before I go too far, I want to make Jack a co-host. Okay, so now Jack has all the superpowers of a co-host. Since we have so many people, it may be worthwhile to do some of the work in breakout rooms, but our main agenda item today together is to just work through some problems together. So before we get going too far, though, I have a couple of announcements. One being that we are having our presentation of the major today, and it'll be a Zoom meeting. I know you're shocked to hear that. You probably got an email from Travis if you checked your email recently about this, with the link in it, and I put the link up here. The most important part, of course, is this meeting ID number to get on that meeting. Uh, that's going to be well a good chance to find out what a physics major is all about. And well, I think that people don't always come to college thinking, "Oh, I'm going to be a physics major," because who's heard about what jobs you can do when you have a degree in physics, out of most any high school. But there are actually a lot of things you can do with a degree in physics that you might not be expecting. So if you have any interest at all, if you feel like over the course of this semester you've built up some skills that you think are really, I don't know, interesting and useful, then I think you should at least consider a physics major or a physics minor, and this would be one way to learn more about it. If you can't come at 4 and you want some information, I've got some documents I can send you about what kind of courses you need to take and so on. The other announcement, of course, being that Travis shifted his office hours to before when the homework is due, but he says he's willing to meet people after 5 o'clock after the presentation of the major if people still like that 5 to 6 time that he was doing last week. As always, appointments are completely welcome. You can have an appointment with me, with Travis. We're probably easiest to catch by email. Um, you can send questions to us by email. I've had a couple of students do that very successfully, and that's been very nice. Tutors are also available by email or by appointment. So if you send them an email with a question, they actually get paid for corresponding with you over the question. Or you can make an appointment. Remember, there's a link near the top of the Moodle page where the tutor hours are listed, where you can just make an appointment on their Google Calendar. Especially if you know, oh, geez, I'm going to be working on the homework tonight, and tomorrow I could really use some time with a tutor. Then just make the appointment and that in advance, and then that way you've got that. With me, I can handle it on shorter notice than the tutors in general. Um, but just remember that those are all available to all of you all the time. Okay. So today I've got a couple of example problems to work out. First, I want to show you some data, do a little bit of data interpretation, and this will be fairly qualitative, but it'll give us a chance to talk about elastic and inelastic collisions. And that's something that we'll see more of. We'll do a lot with inelastic collisions in chapter 9, and then we'll be able to do more with inelastic collisions when we get to chapter 10. And then one thing we didn't do on Monday, we didn't do any problems where we did conservation of momentum in 2D. And I think that's going to be important because there's one homework problem based on that. Okay, so that's the kind of agenda for the next roughly hour, hour and a half or so. Okay, and please do use the chat and type up if there's a question along the way. I'm happy to stop and take on questions. Okay. Okay. So last time we talked really about the big picture, and the big picture item here is that sometimes we have non-constant forces, and non-constant forces are just harder to deal with in in an analytical solution. Um, and we think of those, if I can think of that non-constant force as uh, happening over a short period of time, I can use this concept of impulse to measure like what's the effect of that little force that happened over some period of time. And then we do care about how the force changes velocities of the object, but often it is the case that we don't care that much about the details, okay? And this is typically in a collision problem where they're really, like two things bang into each other and those forces exist only over a short period of time. If we don't care that much about the details of that interaction, and we really just care about what happened before and after, well, then the ideas of momentum and impulse are really um, very handy to have. So some practical things for solving problems. Looking at a problem as a before and after sort of thing um, is pretty essential, especially since we're thinking that we're having the case where, say, the final momentum is equal to the initial momentum. If we want to do that, we'd better do a good job of defining what is the initial and what is the final state of this object. Initial and final have to be really well defined. So be sure you use your pictures to clarify, clearly define the moment that's just before and just after the interaction or the collision in many cases, okay? Another thing you need to do is really identify what the system is. And that can just be a simple statement, something in the key ideas, or something that you say in the pictures, but just be clear about what you're considering the system to be, okay? And the big idea is that interactions within the system can transfer momentum, between different objects in the system, but it doesn't cause the system to gain or lose momentum. It's just transferring it from one object to another, okay? So when you're finding delta P for a system, and especially if momentum is conserved, then that delta P would be 0. Be sure to include every member of that system. And that's the reason why it's important to define the system. So if the system is made up of 2 objects, then you've got to make sure you include mass times velocity for both objects, and with the vector, what direction it is, positive x positive or negative x, and in 2D problems, both x and y, okay? So you've got to include every object in the system, okay? And those are just the main things that stand out when I look at when people try problems for the first time with conservation of momentum. It's often one of these things that is the root of the problem. So I just put those up front just as a thing to let everybody know. From Monday, I'm just quickly writing up the definitions for things like the impulse and what is momentum. And the impulse momentum theorem that let us say, oh, this impulse causes a change in momentum. And that was the basis of having momentum conserved in a collision. Because if there's a collision and the impulse that the outside world is having on that object is so much smaller than the impact of the 2 objects hitting each other, then we can say, well, the change in momentum should be 0, and that's gives us a foothold in solving the problem. So that's where those are. I think I pulled this picture up from last time as well, to kind of re-emphasize the idea of this, the approximations you might have to make with conservation of momentum. So for saying conservation of momentum, that's the same thing as saying delta P equals 0, say before and after a collision or before and after some interaction. It's the same thing as saying P final equals P initial for some system, right? Strictly speaking, it means there's no net force acting on the system, at least in the direction that you're worried about for momentum. But very, very often you'll use that approximation called the impulse approximation. And it's just going to be really, really, really important on your problems, because sometimes you'll have problems where stuff is happening before the collision, and you won't always have a situation where acceleration is zero. But you might be able to say, well, right before this collision, at least I know what the velocity is at that moment. And then right after the collision, if we can think about what would be the velocity right after the collision, and then, you know, during this time after the collision, stuff might be happening. You know, there might be, acceleration could be not equal to zero. But it's really important to make clear in your problem solving, you know, what is the moment or moments that you will consider before the collision, and really it's just before, and I'll say collision because most interactions you can at least think of as a collision, just before the collision and just after, okay? And those are things that I wanna make sure we concentrate on when we're kind of setting up a problem, okay? So does that much make sense so far? Yeah, I'm not seeing much going on in the chat. So um, let me do one thing. So let's do something qualitative first. Here. I'm going to go put into the chat a link to the blog, or you can pull up the blog yourself if you're that nimble on uh, on our website. Here's a link to the page that has some air track movies. So let me pull that up and you can have it here. And this is Travis and I having a lot of fun over spring break. And I don't know if you've had a chance to see those movies yet or not, but take a moment right now to take a look at them. They're not very long. The top one shows you what Travis calls a bouncy collision, and I would call an elastic collision. And I'll play it here, but I suspect you won't be able to um, see it as well. And yes, it is really fun saying boing, boing, boing. Okay. Um, and so in that case, you can see when he was close up that there were a couple of rubber bands. And when the two um, carts actually hit each other, the rubber bands are what was hitting each other in that case. On the second video, we swapped out the rubber bands and we have basically a little clay and needle setup. And that's how we achieve what they call an inelastic collision or a sticky collision. So there's different notations that different people, or different words that different people use. So if you've listened to some of Travis's videos, he'll often use the term sticky for the inelastic and bouncy for the elastic. Your text tends to use elastic and inelastic, so I'll try to use those terms. But what I'd like to do is at least work through one problem that involves collision. Oh, sorry, I want to go back. I want to go back. Oh, sorry. I want to go and look at the LoggerPro data of the collisions that you just watched. Okay. Sorry, I'm getting myself confused. So let me move some things around here. My desktop, I'm going to stop sharing this little iPad and I'm going to start sharing. There we go. I'm going to start sharing my laptop screen here. And my laptop screen shows some LoggerPro data. So I've got a question for you to think about for a moment, and then maybe I'll start asking people on the participation list um, about what they think. But we've got two gliders. They have very similar masses, 210 and 209, well, rounded up to 210 grams. So two gliders. Um, glider 2 is the blue, and glider 1 is the red. Okay, and this is a graph of velocity versus time, in case those letters are a little hard to see because they're kind of small. So um, having seen the videos and kind of know the system that I've got where there's that little cushion of air that prevents the friction from keeping these gliders from moving. Um, tell me what you notice about this set of data. Things like, well, describe what each part is doing and when do you think the collision happened on here. So maybe about a minute for that. Okay. Alrighty. Um, so I'm just going to go around randomly kind of asking, and it'll depend on where you appear on my screen when I check in with you. But I see Piper up there in the top, the northeast corner for me. So Piper, is there anything you notice about this data of these two gliders?
Right, so they have super similar masses, and what appears to be going on is that the blue cart has a velocity, there's an interaction between the two carts, and then the red cart has velocity. So what I think is going on is that there is an inelastic collision because, no, sorry, an elastic collision because if it were inelastic, they would have the same velocity at the end.
Oh, okay. Okay, great. Jackie, did you notice anything else about it that to add to what Piper um, told us?
Um, all I could really add is that I think that the collision probably happened a little after 2 seconds because that's when they switch. That's when
Oh, okay.
the blue line goes to 0 and the red one goes up to
The line
0.5.
goes to 0 and the red line goes up. Okay, do you agree that this is probably an elastic collision?
Yeah.
Okay, all right. How about Chloe? Do you have anything you'd want to add to that, or do you agree or disagree?
I agree with that, and I also think that the momentum is kind of conserved before and after this collision, because the velocity, if like the p equals mv, and they have similar mass, and the velocity, like they have the velocity before and after also kind of around 0.5 meter per second. So momentum is
yeah, very, very good, very good. So I think that's absolutely right. Let me think if there's anything else. Maybe I'll just ask one more student if there's anything else. Then I want to loop back to what Chloe mentioned. How about Sarah? Sarah, is there anything you would add to what Piper and Jackie and Chloe mentioned about this? Is there anything else you noticed or?
No, I think they covered everything I noticed. If you want to be really specific, I think that the red is a little bit smaller than the blue just because some momentum might have been lost, but yeah, I think that can be human error and or a bunch of things that come with doing an actual experiment.
Yeah, yes, it very much could be. And I've done this kind of experiment a million times before, so I could rattle off a list of things, but you haven't had the opportunity to do this kind of experiment, so I don't know if you could rattle off the same list. But that's a nice observation as well. So there's something I can do here in LoggerPro that if you were here and doing this lab, I would have you do. And that is, I can actually make LoggerPro calculate the total momentum as a function of time. And I'll show you quickly how it's done. I'm never going to ask you to do it, So don't worry if this goes by fast, but I want you to understand what I did to make the graph that I'm going to show you next. So I opened up the window for the data, right? And as you probably remember, when you take Sonar Ranger data, you get a column for time, you'll get a column for X, and since I have two Sonar Rangers, it's giving me two columns for position. There's X1 and X2 for the two different carts, for the two different gliders. And then each time it measures X, it automatically calculates V and A for you. Same thing for the second. So the red data and the blue data, those are all just the raw data from the Sonar Rangers. And what I did was I made something called a calculated column, which you could do as well if you like. But there's a calculated column, basically, I had to give it a name. And because I have no imagination, I called the momentum for glider 1, I called it P1. And then it gives me a way to put in an expression of an equation for it. So this 0.2105 is the mass in kilograms, right? Because that was 210.5 grams. And then this velocity 1 with quotes around it refers to the column of data, velocity 1, that was already existed. So I have now a column of data that for every moment in time has calculated the momentum for glider number 1, which is cool, right? Because that means I don't have to get out a calculator and do all that punching in and possibly make mistakes. The same thing for P2, only now I've used the mass of the second glider, which was 209.8 grams or 0.2098 kilograms, times velocity 2. And this may seem like it's the height of laziness, but I also made a column, this orange one, that was adding together P1 plus P2, because if my system is the two gliders, then I'll want to count the total momentum of both gliders all together. So that's something that I did, and I hid that graph a little bit because I didn't want it to be the first thing you saw. But let me move my graph around. Now I've got this nice graph. Oop, come on. Let's move it. And maybe I'll leave that one being big. So if we look at that, P1 is blue down here. And that kind of looks a lot like that velocity curve did. P2 is the green, okay? And that looks a lot like the V2 curve did, which I can actually still let you see. And then that orange one is the total momentum, right? And depending on how closely you squint at it, there's a bit of variation over here, but you could say, well, the momentum over here before this collision happened seems to be about the same as what it was afterwards. Maybe it's a little bit lower. So maybe I've got some interaction with the outside world that's taking momentum out of my system a little bit. But by and large, it looks like it actually seems to conserve momentum, at least roughly. And we could do things like find the statistics for the total momentum before the collision. And we could come over here and find the statistics for the total momentum afterwards. And we could do a T prime, which I'm not going to use our time today to do a T prime, but the mean is actually pretty close. So 0.103 for the after the collision and 0.110 for before the collision. And without comparing that to uncertainties, I don't know if that difference is significant, but it's certainly not very big. So very good. I'm happy with what you're able to interpret out of those graphs. Okay, so of course, Travis and I, one collision is not enough, right? So I'm going to save that, and then I'm going to go to another set of data we took, number 3. So this is actually our third experiment. I skipped number 2. We did a lot of experiments, but I think 3 is probably enough for us to talk about. This is very similar, although I think things might have been going in the negative direction instead of the positive direction. But the one thing I want you to notice here is that the masses are not the same over here. That one of the masses is 311 grams instead of 210 grams. And we can do that because you can put these little masses on the sides, like luggage on the coat rack or something. So we made one of the two heavier. So looking at this velocity graph and or the momentum graphs, take a minute to look at those, and I'm going to ask you again what you noticed about those, and I'll call on different people this time. Although you're all moving around in my little Brady Bunch window, so I'll have to be careful to remember to ask around the room and not just ask the same people. Okay, so how about, let me start on the other side. I see Anna is up there. Anna, can you tell me something you notice about either one of the graphs?
Yeah, it almost looks like for the velocity one, like the first one is almost like pretty constant, like the velocity is almost zero, the blue line, and then the other one is moving. So like the total momentum on that first part is just maybe just gonna be more or less the momentum of the red line, and then after the collision happens, it's like they sort of like exchange, but the red line still has a bit of momentum because it's the velocity isn't necessarily zero like what was happening with the blue line at first. So I feel like there is a collision, but the red line, like they move over different speed. The red line still has some speed, it still has some momentum, and the blue one also has some momentum.
Oh, okay. Oh, okay, great. So the beginning looks kind of similar to the other one, where one cart has zero velocity, the other cart has a non-zero velocity. Then they seem to have a collision, and then afterwards they both have some velocity. It's not that one of them went to zero or anything like that. Okay, Celine, how about you? Do you have anything else you noticed about that or want to add to Anna's description or Anna's description of this?
Yeah, in the bottom graph, you can kind of see how the momentum is still conserved throughout because the little momentum, like even though it's like wiggling a little, it's still pretty consistent throughout.
Oh, okay. All righty. Have I talked to Heather yet? Not yet? Heather, do you have anything that to add to what Celine and Anna said?
I was noticing the same things as them, but and I think it's also still, it just looks like the same situation to me, except now it's just in a different direction.
Okay. All right. Well, let me throw out one more question here. Do you think this collision was elastic or inelastic? So I'll throw that one out, and then I'll call on some people quickly, and you can say pass if you want to. But Joyce, do you have an opinion on whether this collision is elastic or inelastic? And
I think it's elastic since they're not moving together in the end.
Very, very good. So they have different velocities here, and you're saying that if it was inelastic, they would be stuck together and moving together. And here they clearly have different velocities. They can't be moving together. Okay. Yeah. Yes, very good. So by changing up the mass, we made it look a little different, but it's still fundamentally an elastic collision. Okay. Okay, very good. So I'm going to go to my last set of data for you. Okay. So this is another set of data, and the mass of the carts is the same here. On the right-hand side, it's still 311 and 209 grams. And I've got the velocity versus time and the momentum versus time graphs up here. And let me go, I think I've not asked Theo a question yet. So Theo, can you tell me something? What do you notice about these graphs?
Yes, so this would be like an elastic collision because like they will have a similar velocity after the collision. And like initially one like what the first mass would be at rest and the other one was in motion. The blue line was at rest and the red line was in motion. Then the magnitude of the velocity of the red line would decrease because there would be an increase in mass, because when they like once they're together the mass will significantly increase, and which decreases the which decreases the magnitude of the velocity of the red line, so it would be inelastic.
Okay, so when you say the mass increases, the mass that's moving increases. We didn't create mass somehow, we just picked up some mass along the way and it carried it along. So in that sense, yeah, the mass increase. Jasandra, do you have anything that you notice about these graphs?
Also, as what, like in terms of it also being an elastic collision?
Yes, it's definitely so you noticed it was also an inelastic collision. Was there anything in addition to that that you noticed that that you'd want to share?
I do notice that like in the bottom graph, they're slightly like they have like kind of different like momentums.
Oh yeah, that's very good. So and which feature on the graph is telling you that? Like what like, part of the graph? What's telling you that?
When I see when I see both the all three lines, I could see that they all, so basically when they all before the collision will occur, they seem to have like similar level, like when I mean similar values to the velocity, and then so when they actually start to actually come into contact, that's when the lines actually kind of start to split apart, which contradicts the top graph where they actually are touching each other.
Ah, okay. So you're noticing that the red and blue lines in the top graph are more or less the same line with some variation. But you're saying down here, for the most, I mean, if you get away from the moment of the collision, that one of the two carts, cart number 2, seems to have a smaller magnitude, about 0.05 kilogram meters per second for its momentum, somewhere around there. But cart number 1, which is blue on this graph, seems to have a larger magnitude of momentum, and that those two don't overlap with each other. Oh, that's a great observation. So let's run with that. I think I already talked to Jackie. Serena, I don't think I've talked to you yet. Do you have either an observation that you made or something to explain Jasandra's observation? Like, why is it that they seem to have the same velocity, but they have different momentum? So your pick, which way you go.
I think that the reason for that feature on the momentum graph is because even though the final velocity is the same for the system, each individual object has a different mass. So I'm guessing that the green line represents the momentum of mass 2.
Oh, yes. And I don't know how well it shows up on your screen, but the P2 is in green over on the side. So the green line, in fact, does represent the momentum for mass 2.
Cool.
Okay. Okay, great. Does that make sense then? That the one with smaller mass actually has smaller momentum, even though it has the same velocity as the one with the larger mass. Let me go one more. So Lucy, when you look at this, is there any other observation that you can see that somebody hasn't mentioned already?
I think most of it was mentioned, but I could say that maybe a reason why there's in the first graph the momentum momentum, the velocity is not the same, is because of the mass or friction.
Okay. What about conservation of momentum? Do you think that this inelastic collision conserved momentum, roughly?
Yeah, yes, it's very wobbly in the orange, but it's about the same.
Yeah.
It's like about, it's consistent.
It seems roughly consistent, given we've got a bit of noise sort of in the data. Yeah. So it doesn't matter if the collision is elastic or inelastic. That collision should conserve momentum. And that's the thing that I wanted you to see, that even though one of the cards loses momentum, one of the cards gains momentum, it does so in such a way that the total momentum of the system is in this, I mean, albeit experimental system, is kind of conserved. Okay. So let me think, I'm looking out here. There are some people I haven't called on yet, so I'm sorry I didn't get to you. But maybe when we get to the next part, I'll remember who I didn't call on and call on you for that. Okay. Okay. So I'm going to switch back to my iPad screen. Okay. All righty. That down here. There we go. Okay. So great. So we talked a little bit about elastic versus inelastic collisions, and honestly, in chapter 9, we'll do mostly. I don't think we'll do any elastic collisions quantitatively. For elastic collisions, we need one more thing to do it quantitatively, and you'll read about that in chapter 10 for next week. Okay, so that's a little preview. And if you watch Travis's video, he calls elastic collisions bouncy, and he calls inelastic collisions sticky. Okay? All right. So let's do an example. Okay? So I've got an example here where I have a 1,000 kilogram car, and I'm going to start giving these variables names. I'll call that M1. It's moving west at 20 meters per second. I'm going to call that V1. And it suffers a head-on collision with a 1,500 kilogram truck moving east. So I'm going to call that one M2. You can see I have no imagination, so I just keep giving things, you know, subscripts for their names. And we know that truck is moving east, but we don't know how fast. Okay, so I'm going to reserve V2 will be the velocity for M2 because I just want to keep my subscript straight. So the two vehicles become entangled and they skid off as one big clump. They slide a distance of 3 meters to the east before stopping. If the kinetic friction coefficient between the tires and the road is 0.6, so I'm going to call that mu k, how fast was the truck going just prior to the collision? Okay, all right, so a lot of information there. The one thing in the back of my mind is, though, how do I make a helpful picture here? Because I think on conservation of momentum and conservation of energy problems, which we'll get to next week, having a helpful picture is really, really important. And the idea that these problems are solved like momentum before an event is equal to momentum after the event, I want to kind of make my picture reflect that. So if I say kind of before the event, and I'm going to say actually just before that collision, I had, let's see, M2 is the one going east. So let's let this be east, and that'll be my x direction will be east there. M2 is going to the east with the velocity v2, and just before they collide, M1 is going west, and it's got a velocity v1. Okay, so just before, there's my situation. Now, the next part I'd want to go just after the collision. Okay, just after the collision, I've got M1 and M2 all tangled together. I'll call it M3 with the idea that M3 is equal to M1 plus M2. So I haven't really given myself a new unknown since we know both of those masses. I've got M3, which is both of those two things all crumbled together. And I know it must be going a velocity. Let's see, it says it slides to the east. Oh, so it had better be going in a direction to the east. And I'm just going to label it V3 just because I really love my numbering system where the 1, 2, and 3 are kind of sequential there. So just after the collision, it's moving. Let's see, and then it tells me in a little bit, or I'll say in a little while, because that sounds more professional. In a little while, I've got M3 sitting there at rest. And what did it take to get there? Well, it took about a distance of 3 meters sliding, okay, to get from just after the collision to after a little while that it's at rest. So what kind of key ideas do you think we need to have here? Well, I think I've sort of set it up so that that conservation of momentum, like just before and just after the collision, might be important. So I'm going to write that, conservation of momentum. And there might be some other things, I suppose. But let's go back and put more things on there later. I'm just so excited that I've got like a just before and a just after. Let me see what I can do with that. So before the collision, I can figure out what's the initial momentum. And that initial momentum would be, let's see, M2 times V2 in the positive direction. And then, see, I wrote this V1 here going to the left, and V1 is the magnitude. So I'm going to just explicitly, I'm going to put the minus sign in here and say M1 V1, and then I'll make a note for myself that these are magnitudes here, and that I've already taken the minus sign into account to account for the fact that one's going to the right and one's going to the left, okay? So over here, just after the collision, that P final would have to be M3 times V3, which is the same thing as M1 plus M2 times V3. So if I use conservation of momentum, then I can say initial momentum has to equal the final momentum, so that M2 V2 minus M1 V1 has to equal, let me lastly that, let me take that. Oh, there we go. And not only to let me, I'm gonna have to go back one. There we go. No, I'm not that handy with my iPad. I'll have to write it out, I think. Equals M1 plus M2 times V3. And let me use another color to kind of set that one off. Equals V5. Okay. So if I look at that particular equation, let's see, I know M2, I don't know V2, I know M1, I know V1, M1, M2, I don't know V3. So here I am in a situation with one equation, two unknown. So I must be missing something, right? And it occurs to me I have not used the information that after the collision they slid for 3 meters before it came to rest. So now off to the side, and maybe I'll do it over here in blue. If I've got this object M3 that's slowing down to a stop, so V final equals 0 and V initial equals, well, what it started with would be V3, wouldn't it? So it starts at V3, ends at V equals 0 because there's a force acting on it. If I were to draw a nice free body diagram, I'd say, well, those cars certainly have an Fg, gravitational force, and they certainly have a normal force. But now that they're sliding, they also have a frictional force. And if they're moving to the right, then that frictional force has to be to the left. But this is okay because this is the kind of problem that you know how to solve really nicely. If I do my Newton's second law equations, I get that the normal force, Fn minus Fg equals 0. So I'm in a nice situation where the normal force is equal to mg, so m3g. So that's one of my Newton's second law equations. And my second one says, well, my net force is to the left. That would be F net is equal to Fk, which would be MAX. Okay. Now, let me see if I've got my signs right. They both should be to the left. Then Fk is technically to the left. So this will give me acceleration that's negative, and in this coordinate system that I'm using here where x was positive, going to the right, that'll give me a negative ax. That'll be fine. Okay, so just as I'm thinking ahead, ax will be negative. So I'm feeling good about that. Okay. So I can actually figure out that ax has to be, I think I need to give myself a little bit more room. So ax has to be, let's see, fk over m. And which m is that? Well, that's m3, because I'm talking about after they've collided, right? And fk is mu fn, so again over m3, and I gotta keep remembering that minus sign. So that would be minus mu k mg, that would be fg is equal to mg, that's m3, so m3 times g divided by m3. Oh, very happily, that mass cancels out. So I know the acceleration is minus in the negative direction like I expected, uk times g. And since I know a number from uk and I know a number for g, I'm all set there. Does knowing that ax give me any help finding either v2 or v3? And to that I would say absolutely yes, because we can use kinematics. In fact, we can use the constant acceleration kinematic equations, right? And so for that, what do? I know the acceleration, I know how far it slid. If I call that a delta x, I could use that one kinematic equation that doesn't have time in it. So I could say the final velocity here squared minus the initial velocity squared is equal to 2a delta x. Okay, now this final velocity was actually 0 in my kinematics problem. And my initial velocity was the same thing as v3. So v3 squared. Okay, and then 2 times my acceleration, which was negative, minus uk times g times delta x. So now I've got enough information to find v3. And if I do a little bit of algebra here, the minus signs cancel out. And then I've got 2 uk g delta x. Oh, and I shouldn't have put that. That's a mistake. There we go. So just v3 by itself. So we have numbers that we can put in there. And when I put in numbers earlier, I got 5.9 meters per second for V3, okay? Which makes me very happy because now if I go back up to my red equation, I now know what V3 is. And I could solve this red equation to get the thing I really was asked for. I was asked to find V2. So I'm gonna dot off that little space there. And maybe I'll change colors. I'll change to black because I'm getting real seriously close to the end of the problem here. So if I'm looking at this one, M2, V2 minus, minus M1, V1 is equal to M1 plus M2 times V3. Then I want to isolate V2. I'll put the M1, V1 on the other side. And that will give me V2 equals M1 plus M2 times V3. And then there should be an M2 over here next to the V2, but I'm just going to divide both sides by M2 and move that over. And it might look kind of complicated, but all of these are numbers that we know. And when I put those in, I get 23, oh, and I kept 3 sig figs for some reason here, 23.2 meters per second. I think on this one, the 5.94 is what I got when I kept 3 sig figs. Okay, so it looks like I've gotten to the point where I've answered the question, how fast was the truck going just prior to the collision? So it might be good to identify some things here that this was my find. And that under key ideas, I actually ended up using kinematics and Newton's second law. So I'm going to add that in. And maybe I'll even abbreviate it with a favorite way of saying constant acceleration kinematic equations apply. They apply because the acceleration is constant because the force is constant. Okay. Alrighty, so I think the last step here would be to assess, wouldn't it? So let's try and do an assessment. Okay, so here's something where I want to toss this out to you all and see what ideas do you have about what would be a good way to assess this problem. You can think about it for just a moment, and let me call on folks. And I take it, Jack, I'm not seeing the chat window myself. So is there anything going on in the chat window I should know about?
I think we're all good.
Okay. How about this? How about for the assessment? Since we have so many people, why don't I put you in some breakout rooms just to talk about an assessment? How could you assess this problem? Does that sound like it won't take us too long? It'll just be a short breakout room period here. So when you go to the breakout room, though, you won't be able to see my shared screen. Okay, but I think you've all been taking notes, so I hope your notes will be enough. Breakout rooms. Here we go. And I'm going to make 5 rooms, so that's about 4 people per room. So let's do that, and then aim to come back in about 5 minutes. Did you all get invited to a breakout room? Or did I mess that up somehow? Okay. Breakout rooms. Oh, okay. Thank you. Good. Now I've opened the rooms.
Direction, but like, I don't know.
How are we doing? Just thought I'd come check in. I didn't mean to make everybody go silent.
We're doing okay. Yeah.
Okay. So you've got some ideas to bring back to the main room? Okay, then just make sure everybody is kind of, well, all be on the same page about every single thing. But I don't know who I'll end up calling on. Probably somebody I haven't called on yet. There's a couple people in here I haven't called on yet, so so it could be you. I'll go check in with another breakout room then.
Terms of like if we substitute the kinematics equation into the momentum conservation equation, we can see that like the velocity that we found is directly proportional to the distance covered, which I think would make sense considering that like if we have a higher speed, then we can like if the collision happens with an object
This is the quiet breakout room.
Oh. We talked about it and then we just went
Yeah, I've been
quiet.
floating around to different rooms. But you have some ideas of how you might assess this?
Mm-hmm.
You have like questions, or should we just meet back in the main room and collect everybody's ideas together?
I don't have any questions right now.
Okay, all right. Well, why don't I pull everybody back to the main room since it's been, we're at about the 5-minute mark. Okay, see you in a few minutes. Okay. All right. Well, it looks like everybody's back now. So I apologize if I yanked you out of your room when you were having a good discussion. I got to listen in mostly on a couple of different rooms, and it seemed like people were making some progress, even if people didn't necessarily get to a full and complete assessment. But let me go around and see if I can remember. I don't remember talking to Elora yet. So Elora, the group you were in, did you have some ideas? What kind of ideas did you have about how to assess this?
Yeah, I don't think any of our ideas were like, I don't know, super defined. I think assessment is something that I generally, if not struggle with, don't feel like I've really got it high quality. But we were talking about looking at the equations that we made, especially for the kinematic equations, and just making sure that all of the variable relationships are good.
Okay.
And then we were also looking at the masses like M1 and M2, seeing that they were fairly similar, and so that the velocities are pretty close. I don't know, nothing seemed wildly off.
Okay. So if I were to I'll use green here. And am I still sharing my screen with everybody? No, the screen share is gone. So let me put my screen share back up with my iPad. There we go. Alrighty, so now you can see my iPad, right? Yeah. So so what I'm hearing you say when you say the kinematics ones, that kind of ended right here with this one that's still in symbols. And then we use that over here to figure out V2. So if we kind of could say both of these equations make sense, then we can say my answer makes sense. Is that one way of putting what you all were talking about?
Yeah.
Oh, okay. Okay, great. So let me see. The next person I recognize, Elizabeth. Did whatever room you were in, did you kind of take that sort of approach?
Yeah, we used that way to assess the magnitude of our velocity. But as for direction, we said that since M2 is larger than M1, so it would make sense that when they collide, because they both slide east, so it would make sense that the direction of the velocity is also east.
Oh, okay. So you went back and said, well, if V2 was about 23 meters per second and V1 was 20 meters per second, and the thing ends up going east, then the velocity V2 had better be bigger than 20 meters per second, or else it's not going to end up going east, or maybe much less likely to go east, but you've got a little bit of mass advantage there. So 23 times a bigger mass going to the east kind of makes sense in that situation. Okay, that's very good. Let's see, I think I talked to Serena already. Did I talk to Tiffany? So Tiffany, the room you were in, was your room taking the approach of assessing the kind of the number generally, or the equation more specifically?
I think I don't really understand what they're talking about inside, so I wasn't really sure. So.
Oh, okay. All right. Oh, that's fine. Let's go on then. I think I haven't talked to Angela yet either. Angela, was your room talking about assessing the equation or about the value?
Yeah. Talked about similar things.
Okay. So if you were to make a good argument as to why this equation for V3, this V3 equation, why does that make sense? Do you have at least one thing about this equation that makes sense that you might use for an assessment? Meaning you compare what do you expect in the situation to what the equation actually says. It's okay to say pass if you're not ready for that.
If you increase delta x, velocity would increase.
Yeah,
which makes sense.
That. Yep. Go ahead.
That's all I got.
Oh, well, okay. So in this situation, why would you expect that the V3 would be bigger if the delta X were bigger?
Because traveled more distance.
Uh-huh.
So the velocity would need to be higher.
Uh-huh. Okay.
Or travel more.
Okay. All right. Because, you know, all other things being equal, with the same frictional force, same accelerate or deceleration, slowing down, same amount of acceleration, then you'll need a bigger distance to if V3 were bigger. Or if it took a bigger distance, it means V3 must have been bigger. Okay, so yeah, so when you're talking about what you expect in the situation, something about the physics of the situation is a good thing to mention. Let's see, and we could go further with mu k were bigger and so on, but let's go back to the masses up here, this V2 equation, and I don't think I've talked to Nina yet. So Nina, can you tell me anything from this V2 equation? Does it make sense with the masses the way they are, that V2 would be having this dependence on mass? And you can pick either mass you like.
So the question, why like V2 has a dependence on the mass?
Yeah, or does the equation we have make sense? And it looks like M1 is in the numerator and M2 is in both the numerator and the denominator. Pick one of those and see, does it make sense that it behaves that way?
Okay. Yeah, I guess I'm a little bit confused on that, because I'm like thinking about it. Like V2 is like dependent of like the massive one, and like V2 is happening before like V3 occurs. So I guess looking at just, sorry, as a fly, if there's like just the equation itself, to me is kind of like counter. It doesn't make much sense, because thinking like, oh, V2 should just have dependence on like mass 2.
Oh, so you're saying V2 should really only depend on mass 2?
No, like that's like, I don't know, like looking at it like firsthand how I feel about it, but I understand like getting it from like conservation of mass and where that like comes in from, and that like how like momentum is conserved. So it all should be like dependent on each other, like in looking at conservation of mass. But
right. Well,
yeah.
I was intrigued by one thing you said, that did you actually say, you said that V3 should depend on the mass?
V3 should depend on mass. I didn't say that, I think.
Okay, good. Okay, so because that velocity just depended on kinematics, and they don't tend to depend on mass.
Yeah.
Okay, but it turns out V2 here does depend on mass. And let's just, I think M1 is the easier one to think about. M1 plus M2 over M2 times V3. So we talked a little bit about V3 already. Now what was M1 again? Well, M1 was the mass that was going to the left. And if we're talking about the mass that's going to the left, what if that mass were bigger? Would we expect that, if that were bigger, in order to have everything else turn out the same, would V2 have to be bigger?
If the mass were to increase?
Yeah. We'd agree about this with a bigger M1, and we wanted to get the same result, all other things being equal. Would V2 have to be bigger or smaller?
V2 would increase if like the mass were to increase.
Yeah, so in the real world, we'd expect for this collision, if we wanted everything to work out the same way and had a bigger M1, we would need a bigger V2. And if we go down to our equation it has M1 in the numerator. So V2 will always be bigger.
V2 is missing an extra terminology. It's to add M1 and V1 too, all over like the mass too. Or is that V3? Okay, wait.
Yeah, so we took into account like M1 and V1 and then the two together when we got the equation for V2.
Okay, just people in the chat are saying that the equation is missing one term.
Oh, which equation is missing a term? Uh-oh. It's certainly possible. Jack, do you see a missing term? And let me see if I can pull up the chat, because that's, oh, it was hidden behind my other window. Okay.
So Anna put in the chat idea, so they noticed a term was missing. Do either of you want to say where?
I think so. If we go onto that equation, the one that you have on the green box, just on top of that, the full equation, M2.
I see it now. I see it now. Yeah. There's a piece missing from there. You're absolutely right, and I missed that. So how do I fix that up? I'm gonna have to erase a little bit over here, at least a little, and then maybe can I erase? I can't seem to erase some of those things. Uh-oh. There we go. It's not letting me erase. Okay. At least not down there. And not there. Okay. All right, I'll have to figure that out.
It's probably because you're using the annotate function on Zoom.
On Zoom? Am I using the annotate function on Zoom? I had not turned on annotate on Zoom. So I'm actually using my iPad. But no matter. Let's correct it by going up here. I'll just notice that that one's got an X now. So V2 really should be M1 plus M2 over M2. And that's times V3. And then plus M1 V1. Okay? I think that takes care of the problem. That I should have put the M1 V1 over here, and I forgot to write that out before I divided by M2. Okay. Okay, great. Thank you for catching that. Okay. So we have an expression for V2, and M1 is in the numerator. So we know we'll get a bigger V2 if M1 is bigger. But we sort of expect that from the situation that if M1 were bigger, we would need a bigger V2 to keep all other things being equal, to have the same acceleration and V3 afterwards. So that actually checks out. And so M is in the numerator thing, and M1, if M1 is greater, V2 has to be greater too. For all other things to be equal. Okay, so that is one, I think on this one that is a really good way to look at it. What about M2? M2 is a little trickier because it's in both the numerator and the denominator. So you could take this problem and kind of work it in the limits. You could work it and think about what happens as M2 gets close to 0 or as M2 gets really, really big. I'm going to leave that because I'm looking at the time. We're already at 2:17. And I was hoping we could set up at least one more problem before then. So I think assessing this one for the delta x and then assessing this one for the M1 term will be sufficient for this particular assessment. Okay? Are there any other questions or mistakes you noticed that I made on this particular problem?
I think that I think that I probably made an error when I did this, but when I plugged in the values, I got a different value for V2 because I used negative 20 meters per second for M1 for V1. And
oh, okay.
Yeah, and then when I used a positive value, I got the same value that you got.
Right, right. So yeah, so that's why it was important up here that when I wrote the equations out, I said, well, I'm going to use the magnitudes for V1 and V2, and I don't have arrows over them, so those are definitely magnitudes. And the direction I took up here with that negative sign. So if someone else had come through and put, you know, vector signs on top, then they would absolutely put in negative 20 for V1.
Okay. Oh, that makes sense.
Okay.
Okay, thank you.
Okay, great. Okay, let's try and at least set up one more problem, because I think you have a 2D problem on your homework, and it might be nice for us to try out a 2D problem. Okay, so next problem is, I've got a red pool ball that's moving at a velocity of V0 equal to 4 meters per second. So they already gave me the name of a symbol to use here. It collides with the blue pool ball that's initially at rest. And then after the collision, the first pool ball moves off with a speed V1 of 3 meters per second in a direction 30 degrees north of east. And then they ask, what velocity would the second ball have? Magnitude and direction. So this might be another good place to have a good picture. If I start with my red ball, that's moving with the velocity V0. And then if I have I want to say before the collision. And really, it's just before the collision. I've got red ball moving this way. And I think in order for the red ball to move up, I'm going to have the blue ball maybe it's not exactly lined up with it, so that when they interact, this one might get pushed up a little bit. But afterwards, I have that's right before this initial velocity here is 0, and then just after the collision, I have the red ball moving with a speed that I know, 3 meters per second. V1 is equal to 3 meters per second. And I have a blue ball that's moving, well, it's got to be moving down, right, to compensate for the fact that the red ball is moving up. And I'm going to call this, due to my great lack of imagination, I'm going to call it V2. This velocity has some angle theta 2 with respect to the horizontal. And the other thing I know about V1 is it's got a theta of 30 degrees with the horizontal. Okay, so I think I have put everything that's in the problem there. This one is equal to 4. I'll go ahead and put the values on the picture as well, although it's not required. So if I am thinking about my key ideas, if one of my key ideas is conservation of momentum, then I should think about the momentum before and after, right? And here I've got to be really careful with the vectors because this is a 2D problem. So the initial momentum here would be the mass of the red ball. Well, here, is it okay to assume that the pool balls are all the same mass? I think it's actually a great thing to do. So the mass of one pool ball is the same as the mass of any other pool ball. So on here, I'm just going to use M for all the masses. Okay. So our initial momentum would be M1 V0 and it's got to be in the direction of V0, which for us would be east. Maybe that we'll call that the X direction, and then north, which would be our Y direction. Okay. Afterwards, what is the momentum P final? Well, it would be M times V1, as I've drawn it up there, plus M times V2. But these ones have both X and Y components. So just like when we had forces in more than one direction, we split Newton's second law into some of the forces in the X direction, and then some of the forces in the Y direction, and kind of split those off as being independent. I'm going to do the same thing here. I'm going to say, not only would I say that P initial has to equal P final in vector form, but I would have to say P initial in the X direction has to equal P final in the X direction, and at the same time, P initial in the Y direction has to be P final in the Y direction. That this vector equation is going to be solved by actually doing two component equations. Okay. So here we are going to have to definitely go and break these vectors into components. And I think we have enough information for V1. We can say that V1x is V1 times sine or cosine, the X direction, that would be cosine of theta 1, and V1y would be V1 sine of theta. And we could write the same kinds of equations for V2. That might be worth doing. We don't know its magnitude, its angle, but no matter what the magnitude or angle is, that V2x would be V2 times cosine of theta 2. Okay, let me make sure. So 1, theta 1. And then V2y would have to be V2 times sine of theta 2. But here, it's in the negative direction. So I've got to give this a minus sign. Okay? So if I take my two different components and separately do conservation of momentum on those, let's see what we would have. Let's start with the X direction. So P initial in the X direction is, well, there's only X direction. So it's M V0, and that's in the positive direction. That has to be the same as P final, X direction. And over here, there's going to be two components. There'll be M V1x plus M V2x. So I've kind of got one equation here relating the velocity after with the other velocities that we already know. If I do the same sort of thing for the Y direction, I would have, let's see, on this side, initially there's 0, right? There's no momentum in the Y direction initially. And then that's got to equal P final Y-directed momentum, right? So if I go look at my picture again, one of them is going in the positive Y direction. So M times V1Y in the positive direction, but then we've got here some momentum in the negative direction. So that's M V2Y. And so I've got 2 equations. So I'm going to take a look at that and see what do I know? What do I not know? Well, it certainly looks like mass is going to cancel out. So the fact that I don't know the mass is not going to be problematic, because I could just take this top one and divide both sides by m. The bottom one, same thing, and I'll have just equations that depend on y. Now, v0 I know, v1x I know, v2x I don't know. V1y I do know, V2x I don't know. So it looks like I have sort of a classic two equations, two unknown, right? That I can solve that. If I were to solve that equation, I could get a V2y is equal to something, and I would also get a V2x is equal to something. Now, I might have to go take those x and y components and then go figure out what's the magnitude and what's the angle. But once I've got the x and y components of V2, then that's well, easy peasy for you, right? Because you just have to remember what we did back in chapter 3 and what we've done many times since then regarding magnitude and angles of vectors. So V2y comes from that second equation. I think we can say that it's basically got to be equal to V1y. And V1y was V1 times sine of theta 1. And we know both of those, so we can actually come up with a number here. V2x we would get from the x equation, right? And so that would be m0, oh sorry, I did away with the m's. That would be v0, and then minus v1x. v0 we know, and v1x we know that that is v1 times cosine of theta 1, all of which we know, right? v1 no, I was right with cosine. Cosine of theta 1. And I would argue we know all of these, so we can find a number here. And once we know those two numbers, then we would say, well, the magnitude of V2, that would be V2x squared plus V2y squared, square root. Okay, and that one, actually, I'm having trouble finding the paper where I actually sorted that one out. And got the, oh, here we go. In the end, I got an answer of 2.0 meters per second for that magnitude of the velocity. And then theta, 2, that would be the angle whose tangent is what? Up here, it would be the y component over the x component. V2y over V2x. And for that, I got 46 point, well, actually, if I round it up 2 sig figs, then I would have 47 degrees. Okay. And then since we are running low on time, I want to point out something that might not be obvious to you about assessments. And that kind of goes back to our fundamental idea of conservation of momentum. All right, it says that initial momentum and final momentum have to be the same, and they have to be the same as vectors, right? So what if we wrote this out, that P initial, we can actually calculate that out. That would be mass times that initial velocity of 4 meters per second. So it's m times 4 meters per second, right? Then our P final would be m times that 2 meters per second. But this would be at 30 degrees above north of east. Okay, plus it would mass times, oh, I'm sorry, I just wrote the wrong number in with it. Sorry. If it's it should be 3 meters per second times 3 meters per second. This is at an angle of 30 degrees north of east, right? That would give me one of the components, and then the mass times 2.0 meters per second at an angle theta 2 of something like, say, 45 degrees south of east. And we really did this all out with components, but don't we know 2 ways to do vector addition, essentially? We've got one vector is equal to the sum of these other 2 vectors. Couldn't we just draw those out? So if I draw P1, I'm going to try my best to make that be, it's going to have a magnitude of 4m. And then this would be P initial. And if I draw my P final, I need something that is only about 3/4, something that would be about, so it's a little bit shorter there. And that's at an angle of about 30 degrees. Okay. This angle up here is about twice as big. So if this is 3 times m, that would be momentum final for the red ball. And then this other one is at a 45-degree angle, but its length should only be about half of this, at about 45 degrees down. I think I went a little too far there. And 2m. Okay, well, if I add those 2 vectors up, tip to tail, the way they are here, then the total P final looks like it's approximately the same size as my P initial. So because momentum's a vector, and especially in 2D problems, especially for 2D problems, you can just use vector addition as a way to do the assessment. And you can say, oh, look, my P initial and my P final, they're approximately the same direction and magnitude. And for that, I will use a smiley face and leave it at that. So that is kind of all I really planned to do today. We're at about 2:30, which is when I lose Jack. I'm willing to hang around if you have questions, or if you don't, then maybe you will go off and keep working on the homework, and maybe you need to post something for 5 o'clock, or maybe you've got questions about either a problem you posted or a problem that you didn't, or anything at all. So I'm willing to hang out till about 4. Sorry, till about 3, excuse me, and then Travis is going to be here for office hours at 3. So if you still have questions, you can still stay and chat with Travis. So does anybody have any questions right now? Okay, I see people are starting to go. Go Kuro-sama, everybody. You worked really hard today.
Thank you.
So Anna, do you have a question?
Yes, please.
Go right ahead.
Okay, so I was this question is not from the homework blog, but rather from the PSA section.
Oh, okay, sure.
Yes. So I was having trouble trying to understand the. Let me pull it up. I'm sorry.
Oh, okay. Yeah, I'm at the same time. I'm gonna try and find it on my
Okay.
computer and pull it up as well, so I can look at the same thing. Okay. So which problem were you looking at?
Okay, so the one that on the second page, the first one, that's the graphs of impulse and momentum.
Oh, okay. Yeah.
Yes.
It's, two data problems on the second sheet. And
yes,
the first one,
yes,
the impulse and momentum problem. Okay. So great. What was your question?
So I think I had a difficult time trying to figure out like which values to use, because when I calculated my T prime value, I got a different T prime value than the one that you have. And I'm thinking,
was it vastly different, or was it like I'll pull up the answer sheet here. So I think I got something like 2.1 or something like that, right?
Yeah, it's like 2.17.
Right. If you got like 2.2 or 2.3, then
yeah, I did. I got 2.2.
Oh, okay. Then I wouldn't worry about that difference.
Oh.
That difference is probably not big. I mean, it might mean you rounded something differently than I did. But maybe that might not be enough. Can you say, like, how did you determine your values and your uncertainties?
Yes.
Information that's in there.
Okay, so for the impulse, right? I just looked. Yeah, for the impulse, I looked at the graphs, and then I found an average of the two integral values. And then I divided that by 2. That's the average. And then the uncertainty of the impulse, that's the error in the impulse, I subtracted the 2 and found the half of the difference between the 2. That's what I calculated as my sentence. Is that correct?
Okay. So I think that's right. There's a perfectly good statistics box sitting right there. So why didn't you use that?
Well, because the statistics box is like for force, and I'm trying, like, impulse is the integral of force and time. So I just thought that maybe the 2 would be different, considering like the mean are different. Like
yes. Oh, I'm wiping away tears of joy. Yes, that's exactly right. These statistics don't make any sense here. They don't, like, you know. So it's almost as if somebody didn't know what they were doing when they did the analysis. Yeah, whoever put that statistics on there, good luck to them, but it's not really going to help, is it?
Yeah. Oh, okay. Because like I was getting confused. Like, okay, so is that also like the same thing for the changes in momentum? Like that at the box correlation, and is there a place where we use that?
No, I mean, it's a linear fit. The correlation doesn't have any units. There is something there called the RMSE. RMSE is related to G. It tells you how good a linear fit fits to that data with those particular parameters. But does any of that help you figure out a value for average velocity and its uncertainty?
No.
No. See, I put in my best distractors on that question, and you found a way not to be distracted. So that's very good. Yeah.
Then I guess I'm okay then, because I feel like that was my main question. I thought I'd done something wrong. So.
Oh no. Such a small, like usually T prime. I always think of it as something it really only has one sig fig in a way. right? When you get close to 1, I might want to keep 2 sig figs, but really 2.17 and 2.2 are really essentially the same. That means maybe I rounded something down when I put it in my spreadsheet or when I put it in whatever I used to calculate it.
Okay. All right then. Thank you very much. That's my question
You're
for
welcome.
today.
All
All
right.
right. Have a good day.
You too.